morning.
Good morning.
Ladies and gentlemen, and members of the board, we welcome you. We're Team 18. My name is Mark. I have Marco and Alessandro. We are doing a design optimization of a supersonic nozzle. Just a quick intro of a supersonic nozzle. I have here a schematic of a Delaval nozzle. You'll see here that on the blue side here on the convergence section, flow comes in at typical speeds of Mach 0.3, 0.4 Mach speed. It'll enter the throat area where Mach is sonic with Mach 1, and then it'll go to the divergence section, increasing the Mach speed up to supersonic speeds, and then, depending on the pressure, up to hypersonic. Timeline for our presentation, I'll talk to you about our problem statement, our applications, our validation, and some considerations for this project. Now, our problem statement. There are non-uniformities in a supersonic at the exit flow, from the flow at the exit of the nozzle due to upstream conditions such as pressure, temperature, velocity. Also, something that we're going to be looking at is shockwave development inside the nozzle. And shockwave typically starts from the difference of stagnation pressure and the exit pressure. Some of our applications that we are considering is rocket propulsion and also wind tunnel improvements. So, what motivated us? Essentially, optimizing a supersonic nozzle with uniformity, we'll be able to improve supersonic wind tunnels, and also maximizing thrust is something that we all want to see in our rocket propulsion industry. How can we take this project into a global approach? There are many developing countries into space, are going into space. I don't know if any of you remember, but in September, India actually reached Mars on a very low budget. So that's something we're seeing that a lot of other countries are starting to get into space as well. Also, one of our optimization goals, which I'll explain to you in a further slide, is to minimize length of the actual divergence section. That would actually decrease cost and the weight of the actual device. So our optimization goals for this project. So first, we want to minimize the flow separation inside the nozzle. This will avoid shockwave development and decrease any kind of backflow, which would decrease efficiency. Also, we want to minimize the divergence section length. Like I said before, it would decrease the weight and also decrease the cost of the actual device. Next, we want to maximize our exit Mach number, since it would give us a higher velocity and a better thrust. Secondly, we want to also maximize the exit flow uniformity by the exit to throat area ratio, and this uniformity is one of our motivations for the wind tunnel improvement. Next, I'll give it to Mirko about our considerations.
So we're using the Delaval nozzle, as Mark explained. Here's a schematic. We're going to, for design consideration, we're going to be running two-dimensional analysis. So taking this cross-section into consideration. And if time allows us, we'll be running three-dimensional flow. The way we're going to start it is we're going to run equations with isotropic quasi-one-dimensional to obtain initial guesses for our Euler equations, which is basically non-viscous. And then we'll run Navier-Stokes equations, which is viscous and turbulent flow. We're not going to be considering chemical properties in our analysis. As Mark explained before, shockwave location is very important. So we want these shockwaves occurring outside of the nozzle, which is possible, and minimize shockwaves like oblique shockwaves inside the nozzle. We're going to be dealing with compressible flow. As you can see here, we have flow going through the throat, so our density is going to be changing, our flow density. And for our nozzle selection, there are many out there. We chose three that is the most feasible for our project. For our first one, we used the conical nozzle. We designed the conical nozzle. This is the first nozzle ever for Delaval. It's the simplest one to manufacture, simulate, and optimize. As you can see here, there's a constant half angle, which is one of the reasons why it's one of the simplest designs. And in terms of velocity components, if we shorten out this angle, we're going to have more axial velocity. However, our length is going to be much bigger. But if we make this angle bigger, we're going to have a shorter length, but our velocity, there's going to be flow separation. The velocity is going to be coming up and down from this, if you look at this cross-section. Our second design consideration is the bell nozzle. It's the most commonly used design in rocket applications. It has a parabolic shape, as you can see here. It starts off with a large angle, and then it goes down to a small angle for more axial velocity, as well as a shorter length compared to the conical nozzle. It's very efficient at its design pressure, meaning that the exit pressure is equal to the atmospheric pressure. Our third design is going to be the dual bell nozzle. This one is the most difficult out of our three designs. However, it has altitude compensation, so it considers the change in ambient pressure as it raises up in altitude. What happens literally at higher pressures, this wall inflection, as you can see here, will be separating the flow, and it will be treated as a dual bell, as a regular nozzle, as a bell nozzle. And then at lower pressures, you're going to have under expansion, where the flow will be through the entire geometry. The main advantage of this one is its higher overall efficiency at the changes in pressure. However, compared to the bell nozzle, it's not as efficient as the design optimal pressure. For our software, since this is a lot of parameters we're going to be analyzing, we're going to be using multiple softwares. So we're going to design our shapes and meshes. We're going to run CFD analysis and then run it through optimization. For our modeling, we're going to be using SolidWorks and ANSYS. We're going to use initial designs from previous works or designs if we can find them. And then we run the optimization and obtain a final design from the optimization. As for our CFD analysis, we're going to be using this program called Loci. It uses those three equations that I explained in the design consideration. And we're going to be running, as I mentioned before, 2D and 3D flow, as well as hot flow and cold flow analysis. And here I'll pass it to Alessandro to talk about optimization.
For the optimization section of this project, we're going to be using Mode Frontier. It's in a commercially available software, and we're going to use it to meet all of our optimization goals. To basically decrease the computational time, we're going to need to be generating response surfaces, and we're going to be doing that using radio basis functions, and that will greatly increase or decrease the time of computation. Then we're going to proceed to be using an evolutionary-based algorithm to search this surface and come up with our different optimal solutions. The specific evolutionary algorithm we're going to be using is particle swarm, which is both more a robust and quicker converging algorithm than, let's say, the traditional genetic algorithm. For when we actually get to the manufacturing section, we need to consider the scale changes, both what's the scale of our model, the scale of, let's say, the true scale rocket engine or the wind tunnel. We're probably going to be doing this out of plexiglass since we don't have high temperatures. There's going to be no damage to it. And shockwave visualization is very important in our project. Alternative materials will also be considered, taking into account perhaps some problems with the accuracy of this material. Some relevant standards. AS 9100 and ASME Y 14.5 is widely used for quality management in the industry. The first one was developed by the Society of Automotive Engineers. An important consideration is that because of the sensitive nature of this application, most of the standards are completely proprietary or are held by the Department of Defense and are not freely accessible. For the actual validation, we're going to be testing using cold flow from a compressed air cylinder, and that will recreate the internal flow of our nozzle. In our nozzle, we're going to have thermocouples and pressure gauges along the section so that we can calculate variations. And now I'm going to turn it over to Mark.
For our project timeline, since we're in April now, we've done our literary research, and now we're doing our conceptual design and also all our CAD drawings through SolidWorks and ANSYS. These are our responsibilities. A lot of simulation, a lot of analysis and optimization, and we'll get to manufacturing testing in the fall. Now, to summarize our 8-month capstone project, we're here to develop better performing supersonic nozzle. We want to maximize the Mach number and the flow uniformity, minimize the divergent length and the separation, the flow separation, by using analysis and optimization, manufacturing testing using the standards that Alessandro explained, and using cold gas as our primary flow. That completes our presentation, so we open the floor for questions.
You say your temperatures are going to be low. What kind of temperatures are expected?
Well, in the there is a set for the Delaval nozzle. There's a set fluctuation of temperature and pressure. that is in the range of a maximum of about 60% drop from when we get from the combustion chamber to the throat to the exit. Since we are using non-heated air, there's no sort of temperature range that should cause a deformation in the plastic. So it's room temperature.
What is the scale of your sample, your test sample? I mean, the size, overall length, and so forth?
Since we actually haven't had any, so what we're trying to do is, we're going to be doing the analysis part, which is going to feed into the optimization part. And in that section, it's going to be, in that part, once we have the optimization results, we'll figure out what will be our minimized length and our maximum Mach number. So it's all going to be dependent on the optimization software. So at this point, since we haven't done the analysis just yet, we don't have that actual number for the length or the actual size.
I work for an AS9100 certified company, and we spin metal in sizes, fairly large, up to 60 inches in diameter. So if you're wanting to do it instead of plexiglass and aluminum, or stainless or aerospace, heat-treated components, definitely come to us on this, and we can set it up and spin this for you, the different areas. So,
So with the optimization software, how are you selecting your parameters and the limits of your parameters?
Sure. So what we're going to do is that we basically need to see feasibility limits, and that starts before we get to the actual optimization software. So with the low side program, which is where we're going to do the heavy Navier-Stokes modeling, we need to see basically until what point the software converges. Because a lot of typical softwares freak out, basically, with either the velocity or the pressure. The low side program was specifically designed for use in aerospace applications, so that it can handle the pressures and it knows about things like shockwave formation. When it gets into the Mode Frontier program, we're going to be using the parameters that I spoke about before, so that it can search accurately this surface for we can maximize things like exit Mach number, minimize length for a given geometry.
I guess my question was revolving more around, obviously your design intent is to maximize thrust while minimizing length, is what you're saying overall. But to what extent? Because you can maximize thrust and minimize length on something that you intend to be in the 2-foot size, or you can do that on something you intend to be in the 200-foot size. So depending on what ultimately your goal is that way is how you're going to help to define some of those parameters, or else you may not like where they converge, shall we say.
Right. Now, you made a good point, depending on 2 feet or 200 feet, and that's all going to be based on a cost analysis. For us, we've spoken to manufacturer at least, it's for plexiglass. We had a quote of like $500, and we're talking, I think it was a few inches thick. The actual piece was maybe a couple inches in length. So, yeah, maybe we can optimize something at 200 feet, but in our project, there's no way we're going to be able to afford something like that. So that would be a contributing factor.
Right. I mean, there's a difference between the design intent and a working model.
Right.
So that's what I'm saying. What are you limiting your design to versus what you're modeling and what you can simulate and even do wind tunnel testing on? There are methods by which to reproduce that with equivalent forces at a smaller scale. I just want to make sure that you're focusing on the design intent, and then you're focusing separately on the modeling, or the scaled model of it. So that's all.
Along those lines, I have a comment to make, because in optimization, you need some type of baseline model to say, well, this is not working properly, let me optimize it accordingly. You did show 3 models, and is the attempt here to get those 3 models, run them through the optimization and optimize the 3 of them, or is just pick the best one of those and then build it? What's the strategy?
Sure. So we basically run first through the CFD program, all 3 models. So that we can start getting some values that we can input into Mode Frontier. The plan is to optimize all 3 of them. But in the end, the manufacturer will only be up to one best.
I'd like to add that ideally we want to optimize those three. It will depend on our time constraints. We want to run as much as we can. Or based on our optimization goals, we will choose one to manufacture. And also has to take into account, as you said, the feasibility. How is the optimization going to run that? Is it going to go crazy, like the simulation going to go crazy or not? Like the dual bell nozzle, at higher pressures, it's got flow separation. That might actually cause the program to not register real or get real values.
I have a question. What's your accessibility to these, to the software? And also, out of the three, which one is most experienced using the software? Because there's going to be a time lag where you're learning the software to use it correctly and learning how to analyze your data.
Right.
How are you guys attacking that problem?
Well, we have in hand the low slide program already. We were given it by our advisor, so we have that, and two of us are working on it to understand the program. The other modeling programs such as SolidWorks and ANSYS, I have experience, Marco has experience, Alessandro has some experience as well. And he has the optimization experience, so since he took the class this semester. So in terms of the lag time of learning, the only program that we see a little bit of lag is the low side program. But since we have two people working on it, we think that we can be pretty up to speed quickly.
I'd like to add that we also have a summer term, which we took that into consideration, and we'll be working all time summer.
Because I remember when I was going to school here, a lot of times, everything was great in paper, in ideas and paper, but then when you actually put it in application, there's always something that stops you one way or another. And you mentioned multiple softwares that I'm thinking, well, do you have accessibility to all of them, and do you know how to use them? That was my first question. Okay, cool. So you have software already playing with it. Cool.
And do you have the hardware capability to handle the kind of simulation that you're talking about?
So yes, I have a i7 processor. I have the ability to do my specs.
You may want, who's your advisor on this project?
George Dooley Kravich.
Do we still have the parallel computing system? Access to that? Do you know, Sam?
Mike, I think 2 years ago, that's when I used to.
Yeah, I know 2 years ago when I was still maintaining it, but I'm not sure. I think I moved over to main campus. Speak with them. You may have access to a parallel computing system that even with your i7, you're talking possibly days of optimization. So speak with them regarding the parallel system.
Has he upgraded the system from 2 years ago, do you know?
I think
So we gotta talk to him.
Even at that, it was pretty. 300 nodes. It was pretty extensive.
So I have a recommendation. I had a question, but he asked it already.
Oh.
And so for when you're learning loci, when you think you've gotten to a good point where you understand what you're doing, try to find something
To test it.
Yes.
Yeah.
But something that you already know the answer to.
Yeah.
Because
Right.
you may think that you understand it, and you may be getting the wrong answer.
That's
So
part of the validation process.
And so, yeah, just test it before, starting your own
Yeah,
design project.
because there's something about black boxes, man. Us pilots know that.
And use all these resources you have here, because the roll of wind, and I know in one of the labs there's a smaller wind tunnel.
Yeah, they're trying to find a lot of that.
Right.
Tunnel there.
Use all your sources you have here. Okay, cool. Thank you.
Very good, guys.